So the reason behind the higher yield in the convergent synthesis compared to the linear synthesis is, so let's say all steps are giving 90% yield, including in the all the reaction. So let's say we get the 90% yield in this one, 90% in for this reaction, 90% for this reaction, 90% for this last step. So what will be the overall yield of this reaction, the first linear synthesis? You can put into the comment box if anyone know what will be the overall yield for this reaction. The A to B, B to C, C to D, and D to E. So this is basically 90% for each step. So how much it will be? So just multiply by 90, sorry, 0.9 multiply by 0.9. Do this 4 times and then multiply by 100. So this will be the 65% overall yield for this first linear synthesis, right? So how much overall yield it is? 65% in this linear synthesis. But what the same 90% yield is there for this convergent synthetic approach. So this first step gives the 90%, this 90%, and this 90%. So what will happen in this case? So in the first step, we are getting the 90%, and then the second step. So these both reactions, like the reaction of the AB gives the 90% yield. So we have the 90% of these AB in hand. Similarly, we have the 90% of CD in hand. So in this case, we have the 90, or both these are in the 90%. Then if we do perform the reaction on this AB and the CD, so this 90 multiplied by, so this will be overall yield in this case will be the 81%. So that's the advantage of this convergent synthesis. So we don't uh, we get the higher yield in the convergent synthesis. Not necessarily each and every step has the 90% yield. So in this case, in the first, these yields are obviously depends upon the reaction to reaction, and also the yields from this convergent synthesis can also be depends upon the reaction to reaction. But basically, the mostly 99% the convergent synthetic approach is useful for the in the retrosynthetic analysis compared to the linear synthesis. But the difficulty is the obviously the reaction feasibility. So we'll see some examples when we move to the actual synthesis of the some molecules. So we'll start in this first lecture session. We'll see the simple problems, and mostly we'll see some assignment oriented problems. We'll not go in much more detail in this session. Okay, the next important concept is the protecting group. So this is the most important concept in the organic synthesis. So this protecting group is helpful for, let's say we have, okay, we have the compound which has the primary, secondary as well as tertiary alcohol group, and we want to do selectively reaction on the this primary group, or we want to do selectively reaction on the this tertiary alcohol. So reaction like oxidation reaction, let's say. So we want the product. Obviously, the oxidation on this not possible, uh, but on this reaction, sorry. Okay, on this one, the secondary alcohol, the oxidation is possible, right? So let's say we want this oxidation reaction to done on get done on the this alcohol, right? So we can get the product now. Here it will be the ketone, right? So we want to get our reaction done on the secondary alcohol, the oxidation reaction. So we can do this straight directly straight forward, right? Forward, right? Because there is another hydroxy group, so which is highlighted here in the green. This hydroxy group can also get oxidized, and obviously, if you try to do the reaction directly, so what we will get? Where should be the methyl? We can get this aldehyde, or at some point, if we use the strong oxidizing agent, then can be alcohol as sorry acid as well. I just missed one carbon. Yeah. So we can get mixture of product, right? So we can get either oxidation of this alcoholic group, or maybe oxidation of this as well. Both can also oxidize, or also we can get the product in which the only the aldehyde, that's the most reactive, is getting oxidized. So we get the mixture of product in this. Uh, yeah. So we get the mixture of product in this reaction if you directly do the oxidation reaction on this one, right? So what we need to do? So to for selective oxidation, we can do like this way. So what we need to do? We have to protect this remaining reactant hydroxy group to get the selective oxidation of this secondary alcohol, or this alcohol that I have highlighted. So then what we can do, we can use such protecting group which is selective towards the primary alcohol, but that is basically more reactive toward the primary alcohol, but not reactive to the secondary or tertiary alcohol. So we'll protect this alcohol group with this protecting group, and once we protect this alcohol, then we'll do the this oxidation reaction on the another alcohol. So we'll see some examples of this later part. So this is about the protecting group. And there is the last concept in this chemical, retrosynthesis, which is chemoselectivity, regioselectivity, and the stereoselectivity. So this we will see with some examples. So basically, I will show some examples. Let's say, all right. So if you add NaBH4, so where will be the hydride minus? So NaBH4 is the source of hydride H negative. Where it will go? So what are the options that we have? So it can go directly on the carbonyl. Second, it can do the attack on the Michael fashion, that the or the beta position of this alpha unsaturated double bond. So these are the two possibility to attack, and which is governed by the chemoselectivity. So if we are using the NaBH4, so that's the source of hydride. So what are the option? Or the first possibility is can attack on the carbonyl. It react on the carbonyl. Second option is it react on the double bond, and third is the both carbonyl plus double bond. So to get this selectivity, we have to add some additional salt, like the reduction that CL3 or cerium salt, that we'll see some specific reaction later. But yeah, so and also there is again, instead of NaBH4, if you add the LiLH4, the reactivity will be different, depends upon. So in the same case, this is also LiLH4 also hydride source, but the reactivity. So this NaBH4 reacts selectively on the mild soft condition, soft electrophile, but this LiLH4 react on the hard electrophilic side. So mostly the on the carbonyl first, and then the on the double bond. So this is governed by the basically the chemoselectivity. Then there is the regioselectivity. The regioselectivity basically, so let's say we have the double bond, and we are going to do the bromination reaction, addition of the HBr, let's say, on this double bond. So where the bromine is going to attack, so the bromine will be here and the hydrogen will be here, or what is another option? So this can be the bromine on the terminal, and hydrogen will be here. So this will be the selectivity between these two will be the residue selectivity. So if you add the HBr, normal HBr, I should write the H first. If you add the HBr, then the this addition of the bromine takes place on the, whether it is on the less substrate side or more substrate side. It basically tells about the radioselectivity in the reaction. So obviously, this radioselectivity, to understand the radioselectivity, we need to go into the more detail of the reaction mechanism. And what if we add the peroxide, then the addition of this HBr in presence of the peroxide on the olefinic double bond, then the major and minor product will be the different from this among this A and B. So we can basically tune the radioselectivity by selecting the reagent combination. So either by only the HBr or HBr with the H2O2. All right. So these are the some basic concepts that we are gonna see in the throughout this course. And so this course is basically the 12-week course, and this is just a general layout of the course. So if you guys have any curiosity regarding this course, you can ask a question right now. So this is what I have just given the overview of the course. Uh, what are the some basic terminology that we are going to study in this course? And if there any, if you guys have any doubt, then we can discuss that one first, and then I will move to the some of the problem that I have shown here. We can discuss that problem then. Does anyone have any doubt or any question regarding the course or the topic which are here in the course? And also, if you guys want to learn more about the some organic synthesis, I have added some of the reference books in the OneDrive on the Google Drive, and I hope you guys have the link for that one. I will paste that link in the chat box maybe at some point, so you can save that one. You can have the reference book from that one. And also, if you guys want any PDF from any reference book, you can just paste in the chat box. I will try to get available in the PDF format, and I will add that into the Google Drive. Okay. So I will move slowly to the some of the problems. So why retrosynthesis is required? So the first question, why retrosynthesis? So that part I will show with the some actual examples. So let's say I want to synthesize this molecule. So this is my molecule, target molecule, and I want to synthesize this molecule. So how I can able to synthesize this molecule? So this is my target molecule, and how we can synthesize this target molecule. So what the approach that I have used here is, so to synthesize this target molecule, so we'll break down this molecule into the different part. So let's say this is my molecule, and sorry, just somehow just lacking. Yeah. So this is my target molecule, and in this molecule, what you can see, uh, we have to get the simplest starting material to synthesize this molecule. So what are the possible retrosynthesis analysis for this molecule? So it will be, you can simply see, so the this part looks different and this part is different. So this part, these two are connected with each other with this bond. So if we just do the disconnection on this bond, so what we can get, so I will draw this space is A and this space is B, right? So this A and the B that we get with the help of disconnection. So this HBT part, uh, right? So this is the part, uh, we have the, this is the synthon, and another part is like this. And among these two, one will be the positive and one will be the negative, right? So let's say this is the positive and this is the negative, or vice versa. So at this position, it might be the positive charge, and here there will be negative charge. I will draw this C6H13 chain just like with the methyl one, just for simplicity. Okay, so this is what two uh, we get the two parts of this molecule, and they are the synthon. So this A is the synthon, and this B is also the synthon of what will be the synthetic equivalent for these two molecules. So the synthetic equivalent for these two molecules will be, I will draw here only just to save some time. So these are the synthons, right? Hope you have noted. Now what will be the synthetic equivalent? So I will write the synthetic equivalent for this one. So the synthetic equivalent for this one will be the halogen, any, let's say I will draw just bromo. So this is one synthetic equivalent for the earlier that shown. And for this one might be the, let's say, the borate. So this is the synthetic equivalent for the earlier anion that I had shown. So these are the synthetic equivalent. This is also the synthetic equivalent, right? So these two are the parts couples together to form this our target molecule. And if you again do the further retrosynthesis of this the upper part, let's say this hydroxyphenyl benzothiosyl unit, that also we can go into the again in the simple say again to the simple form. So let's say we have this OH and this is the bromo. So this can also be, we can do the disconnection on this one. So if you look at this reaction, what you can see here is, in this case, this is the bond. These are, sorry, the two bond we can break, and we can divide this part, this entire molecule into the two different compounds. And what will be that compound? Two different compounds will be. So these compounds will be this N will be the negatively charged, S will be the negatively charged, right? And this part make comes from, so this is the carbon, the positive charge, three positive charge, right? And this will be the OH, and this is the bromo. Again, these are the synthons. These are again the synthons, right? And what will be the synthetic equivalent for these two individual molecules? So the synthetic equivalent for these molecules will be this NH2 and this SH. So this will be thioaniline, right? And in this case, what will be this one? This this will be the acid, right? So we have broke this molecule into the further simplest and the commercially available starting materials, right? So these are the starting materials now. And so in this way, we can able to get the synthesis of our target molecule done. And if you look at the original synthesis, so this was the starting materials, these two. So they have coupled or the condensed in presence of this PPSC uh, reagent and in the some solvent at some temperature, and we get this hydroxyphenyl benzothioazole compound, the bromo hydroxyphenyl benzothioazole. And this bromo hydroxyphenyl benzothioazole, if just coupled with this boric ester, we have get the target molecule. So this is what this is the linear synthesis. Oh, sorry, this is the synthesis for this target molecule, and we need to analyze the retrosynthesis that we have did in the earlier slides here. So we did the disconnection here, and further we have did the disconnection of this HBT molecule as well. So like this. So this is what. So for this, by doing theoretically this disconnection, I got idea. We can go by this synthetic route, and if you look at so I got the synthesis of these target molecules by this route only, and this is what the initially proposed route that I had, and I got the what I have the theoretically, I got the similar result experimentally as well, and this is the actual experimentally synthesized target molecule, right? So this is another target molecule which is just very similar. Instead of this boric ester, the coupling partner is different. This is the phenyl carbazole boric acid. So that's the, you can see here the part in the target molecule. Okay. If you also look at this boric ester, this can also be broke down into the simplest version. So I will just directly show here. So this boric ester here, this can be prepared from the bromo compound. So the bromo compound, we know the Miura borylation reaction, right? So Suzuki and sorry for the pronunciation, but yeah, the borylation reaction, we can convert the bromo compounds to the boronic ester. So this will be the synthesis. And if you do this one, so this is basically the functional group interconversion from this boronic ester to, if you just go reverse back to the bromo, so this will be the functional group interconversion steps that we have did. And again, so here, so this alkyl part in this bromo compound was added, was not earlier in the starting. So this C6H13, that's basically the alkyl chain like this, and this added from the bromohexane. So you can see here the reagent the from the bromohexane, and this is basically the functional group addition reaction, we can say. Or yeah, or the disconnection also, because the two alkyl chains are the have added. So we can potentially break these bonds between the alkyl chains. So that's basically from the, so this reverse step will be the disconnection. Okay. So we have seen one example, and if you want to more some example here, there is some more complicated examples, but I don't think I should show this on the very initial stage of your this chapter. Sorry, this course. But yeah, I would like to show this some reaction. So you will basically get the flavor of what's why this retrosynthesis is really required. So let's say this is the my target molecule, and how you will think to synthesize this target molecule. So this is just linear synthesis I have shown, but yeah. So this is what the target molecule I had, and I synthesized this target molecule from the you can see this number of steps, and this for to get these steps. Initially, we need to do the retrosynthetic analysis, how we can start this in our synthesis, and theoretically we need to propose some plan, and then we have to move to the actual synthesis part. But if you look at the names that we have studied in the start of this course, the like functional group interconversion or the disconnection, so that we'll just see here. Don't worry about the reaction condition for now. Just focus on the what are the concept involved here. So from this to this, so what this step will be. So if you look at this alcohol, uh, this bond on the disconnection, we get this alcohol. We not directly alcohol. There will be in between O. Yeah. So upon disconnection, we get this alcohol, and further this alcohol. If you look at this alcohol, and this is the ketone. So this is basically the functional group addition, the R group. So if you look at the reagent here, that's the 1 bromo 4 butyl benzene and the butyl lithium. Basically, it forms the anion, and this anion attack on the ketone. So basically, the Grignard type addition reaction across the carbonyl compound. So this is again the functional group of the interconversion. So the keto group converted to alcohol. Then if you look at here, so from here to here, this will be the, if you just do the disconnection here, so we can do the disconnection on these two parts. So the symmetrically on the these parts. So if you just do this connection, we get the uh, dibromo compound. So this is the compound, right? And again, the bornic acid of, sorry, the bornic ester of this part. So that's the bornic ester. And again, as shown earlier, this boric ester can be synthesized from the bromo compound, and this dibromo, sorry, this bromo compound can achieve from this addition of the carbazole across the one center. So we can get this bromo compound 5.6. So this is what we need to do in the synthesis. So to get this synthesis, we have to initially do the retrosynthetic analysis. So we can able to heading towards the target molecule accurately. Okay, so this is what about the all brief overview of these of this course about the organic retrosynthesis, and we are gonna see some problems in this one for today. I think this much introduction is good enough for now. I will directly move to the some problems, and mostly just I will just show here some problem. I don't think I really need to explain these all problems because they are very simple. But if you guys have any doubt, please put that into the chat box, or also you can unmute yourself and ask me anytime. So the final exam will be objective. Obviously, the final exam will be the objective, and it will be the computer-based exam. And the mostly question generally came from the assignment. And so assignment, all the questions generally are the similar. The concepts are the similar. Does anyone have any other doubt? Sorry, I'm not able to hear. I just the volume of my PC was just off. So sorry. Can you ask again? Mm, somehow I'm not able to hear if anyone is asking question. I don't know why. Please use the chat box for today's session. Somehow I don't know what's happening. I'm not able to hear. Okay, I'll move to slowly to the some problems. Mostly these are the problems directly I have taken from the week zero. I will just show you how we can just quickly how we can select this solve this problem. So basically, uh, are you guys able to unmute? Hmm.
Hello.
Yeah, you can. Yeah, yeah, I can hear you now.
Hello.
Yes.
Is myself Dr. Madhumita Hajra. Uh,
Yes. Please. Uh,
I I want to know whether the final examination will be in objective type
yes. Mostly it will be objective type. Yeah. But
or
to
the
solve.
we'll get all the answer from the assignment.
Uh, the similar
If
question
we,
as we see in the assignment, the questions
yeah,
most
yeah.
likely be similar.
Or the assignment each week we have to submit the assignment.
Yes, each week assignment you need to submit on time, and I think the assignment marks also get into the account for the assessment. So there will be some sort of weightage for the assignment as well.
Or may I, if I want to call you personally by phone, may I get the number or anything for the help?
I have added here my mail ID, so you can refer this one. So this is you can contact me.
Okay, okay,
Currently,
okay, okay.
I'm not in right now, not in India. You can see this one. So right now you can't able to even. contact as well.
So
Yeah,
from
you
where
can.
you
You,
are?
uh, I'm in the UQ, basically. You can send me a mail, and from next week I can able to clarify your doubt if you guys have any doubt.
Yeah, yeah, yeah. Okay, sir.
Yeah,
Okay, okay. Oh, thank you, thank you.
yeah. The for all of you, the assignment questions you need to submit. I don't think it will. The assignment will take more than 10-20 minutes to just submit. Just try to submit uh, on weekly basis. So I will show you some question here. So I hope most of you guys are from the masters and above level. So I don't think there should be any issue in the solving this question. So the first question here is this is I just taken from the week zero assignment. So you can see how easy it is. So the following retosynthesis as shown can be achieved by applying. So it's just like you can directly see this will be the by the Beckman rearrangement reaction. You guys know the how the Beckman rearrangement reaction looks like. So yeah, you just need to tick out the Beckman rearrangement reaction. So this is ketone can convert into the amides and by using the Beckman rearrangement. So that's what. The next question is the following retosynthesis as shown can be achieved by applying. So again, the similar. So if you look at this one, so this is a aldehyde. So the birch is forget about the birch and aldol and the canizorous. So this will be the benzoin condensation reaction. So you can see, uh, uh, yeah, right. The for the first question, we got the answer in the chat box. Yeah, that will be great. If you have any answer for this one, just put into the chat box. Also, that will be helpful for just it will be interactive type session. That will be good instead of one way conversation. So the for the first question, the option A is the correct option. Someone have already put it in chat box. Thanks. For the second question, the option C is the correct one. That's the benzoin condensation. Here is the third question. So if you look at the question, the retrocity by applying, I will not read more again and again this same. Okay, so this is what our product is. And if you look at this is the, uh, from the acid, we got this double one. So obviously this will be a burst reduction reaction, right? So in the burst reduction, what is the condition? So we will also just, while the process, we'll just recall the condition also. The sodium in the liquid ammonia. So this is the burst reduction reaction condition, right? Sodium or lithium. And then we add the ethanol after 15 minutes. Similarly, the you can also see the conditions while studying this, solving these problems. Okay, the next question. So the option B is the correct option. In the fourth question, what will be the question? The following retrosynthetic analysis as shown can be achieved by applying. So we have here uh, this is the starting material, and if you look at this one, so the first step will be obviously, uh, if you just do the burst reduction, what we will get? We get the, we get something like this, right? And like this, or yeah, like this, and then if you do the acidic workup, so this basically alpha beta, so alcohol that convert into the ketone just by the tautomerization, right? So this is what the product here, right? So the burst reduction followed by the uh, workup. So this is basically the tautomerization reaction. So I just not drawn this double bond correctly. It should be here somewhere, I think. Here or yeah, but yeah, in this case, I'm not sure the position of the double bond. But yeah, the other options you can neglect other options very easily, and this is the only logical options we have here. So for this competitive exam, particularly the objective type, it is very easy to get to the answer, final answer. In the next reaction is this is basically the elimination reaction. So this hydrogen from here. So there is the hydrogen and this hydrogen. So obviously this for this elimination reaction, it should be the syn side. So this hydrogen and this entire group is eliminated. So this is the Chugov elimination reaction. And the next question is the following retrosynthetic synthesis as shown can be achieved by applying. So this is you can directly see 3,3 Claisen rearrangement reaction. So that's what the Claisen rearrangement reaction. The another here is the Wittig salt and the aldehyde. So so this is basically the Korey-Chokovsky reaction. These are from the assignment question. That's why I'm not explaining too much on this one. But from next week, I will not solve the assignment questions. The eighth question is the following retrosynthesis as shown can be achieved by applying either ozonolysis or Jones oxidation, Solon oxidation, or the Luminous Jones oxidation. So here, I'm not pretty sure about the what is this Loomis Johnson oxidation, but why I go directly to this option because if you look at the ozonolysis, what will happen if you do the ozonolysis on this molecule? So ozonolysis basically uh, deals with the uh, disconnection, sorry, the cleavage of the double bond and the further their oxidation. So the this is wrong. Again, the Sorn oxidation basically useful for the oxidation of the alcohols, but it doesn't really cleaves the bond between. So this double bond, it will not able to cleave that one. Similar case with the Jones oxidation. I'm not pretty sure how this luminous Jones oxidation work, but I recommend you to refer the reaction mechanism. So you can refer the reaction mechanism for this one. I will also cover the thorough reaction mechanism for this one. I will keep that in my note. I will explain this in the next video. Okay, the next question is the following retrosynthesis can be achieved by applying. So here, what we have here. So here there is alcohol we got from this ketone, alpha beta unsaturated double bond, right? And as I have mentioned, so do the if you add the cerium salt with the NaBH4, so that will be the Luce reduction, and that can selectively reduce this alcohol to the reduce this ketone to the alcohol very selectively instead of doing addition or giving the side product on addition on these double bonds. So for this one, the Luce reduction is the correct answer. The next one is the correct product form in the following reaction. So that's what I have shown example earlier. while showing the example of the synthon and synthetic equivalent. So on this starting material, I'll just on this starting, you can see here. So if you add the butyl lithium, basically it is strong base. So it will abstract the proton from this one. So it will show the ortholithiation, right? So OMe, and here that will be the negatively charged. So this will be the first step, and there will be again there is a formylation steps, the B. So once this anion form, so when it react with the H double bond O and Me2, and it will do the formylation reaction, and we get this product. So the correct product in this reaction will be this one. So there are some other examples. I think this is from the current assignment. I should not solve this one, but since it is your first assignment, I will just solve some of the problems. They are like very similar that I don't think you really need to put effort in solving these problems. Okay, the next question is, if you look at here, so this will you can directly see the Kcn addition across these aldehyde. So this is basically, yes, the benzoin condensation reaction. So the similar example that we have also seen earlier, the benzoin condensation reaction. The another questions are, I will take the some questions, not all, but few question I will take. Another question is the product in the following reaction is. So in this case, if you look at here, so this will be a 3,3 sigma tropic rearrangement reaction, right? And what will the product here? So in the chat box, I can see here the option B. We'll see whether it is correct or not. So how the this will goes here, this bond goes, this goes here, this bond goes here, and this bond goes here. So the double bond star, okay, the double bond, and addition to the hydroxy group, there will be a right. So the option B is the correct option here. So this is basically 3,3 sigma tropic rearrangement reaction. So this is what I think almost all questions from the assignments are very similar. The fourth question is about the treatment of the hydroiodic acid on the alcohol, and fifth is also similarly based on the Wittig reaction. So I will not really solve all the questions because they are, I should not solve the questions from the assignment. In the sixth question in the assignment is about the which of the following alcohol could not be prepared by hydride reduction. So if you look at here, obviously alcohol here 3 is not possible to, because there is no any hydrogen on this center. So option 3 is correct here on the question number 6. Then on the question number 7, which sorry, the following reaction will yield the which following product. So this is basically the NaOH and the heat. So NaOH abstract the proton, and then there will be a, so from this one, so the alpha proton is getting abstracted, followed by the Michael addition. So you need to work out to solve this question. Uh, just try the possibility, the aldol condensation and the Michael addition reaction. So that's what you will able to get the product by this way. In the eighth question, so there is like NaNH2 and the butyl lithium, and followed by the H2 and Lillard's catalyst. So basically, this is about the first step, the strong base abstract the proton, followed by the butyl iodide. So there will be alkyl chain will be attached on this terminal of this double bond, and followed by the Lindlar's catalyst give the selectively the cis reduction. So we get the compound option A as a product. So you know the what's the difference between the Lindlar catalyst and the reduction using the lithium and the lithium metal. So if you do the reduction of the triple bond with the lithium metal, then we get the trans alkene as a product. And if you do the S2 and Lindlar's catalyst, we get the cis as a product. Okay. So in this question, why this option A is the correct option? So I'll take it on the PPT later. Okay, in this case, if you look at here there is a proton, and in presence of this NaNH2 strong base, this proton is getting abstracted and it forms the this negatively charged here, and we have now in the reagent the butyl iodide, right? So this iodide is good leaving group. So this is the R group entirely. So this negatively charged attack here, the iodine group remove. So we get the R triple bond and here the butyl group, right? Then we have the H2 and Lidlar's catalyst. So this H2 and Lidlar's catalyst give the cis alkene as a product. And because if you look at this olefin, the H2 supported on the catalyst, this addition of this H2 takes place on in the syn fashion. So therefore, whatever the product we get will be the here uh, cis or Z form. We can say Z is the more appropriate, right? And so that's what, therefore, the option A is the correct option here, not the option B. Obviously, these other options are not correct. Yeah. So among this A and B, the A option is the correct. That is, which contain the Z, the stereochemistry of this double bond as a Z. And I'm saying also, if you have the lithium-based reduction, then in that case, the reduction goes in the radical fashion, and we get the trans or the E-alkene, that sort of product. But in this case, we have the Lindlar catalyst, so we get the the Z as a olefin. I hope you understand this one now. Then there is another question on the some just a similar question on the question 9. Okay, so what happened in this question? So if you look at the what will the major product of? So we have the cyano compound starting material, then we have the Grignard reagent, and then the acidic workup. Okay, so if you do the addition of this magnesium bromide, so it will add on the nitrogen. So this will be the cyclohexyl. I will just draw it here. This will be the N, and this will be the now the entire additional whatever the Grignard part, right? So that I'll just draw here. So just one, two, three, one, two, three, and four. Yeah. So this is what uh, the compound, right? So this is the N, and upon workup, so this N so get converted into the ketone. So this is what, sorry, this is what we get, right? And then the next step is Wolff-Kishner reduction. So basically, what Wolff-Kishner reduction do? So this ketone can directly now convert into the CH2 group. So this will be the H. So this is what Wolff-Kishner do. So the option A is the correct option here. So like this, you should able to solve all the question. Just play with these synthesis on the, take the pen and paper and just try to draw the mechanism. Then you will understand more and more. Similarly, there are 11th and the 12th question. So 11th question is just like BH3THF. So basically the BH3 addition takes place, and then there will be addition of the H2O2, NaOH, and then the PBr3. So obviously this will be the addition of the BH3. In the BH3, you need to take into the account this boron is the electropositive here and the hydrogen is electronegative. So that you need to take into the consideration. Otherwise, you will just directly add the addition according to the Marconi-Crox rule. So B is generally the positive and the H is negative. So that's where the people do the mistake in this first step. So do the addition according to the Marconi-Crox rule, followed by then the S22 addition on the boron, and then there will be PBr3. PBr3 basically helpful for the bromination, so it will replace entirely the boronic group to convert it to the bromo compound, bromo. So there is another few more questions are there, but they are very similar. One question is on the Wittig reaction and the I will take one example, which is based on the basically the protecting groups. So I should not solve all the questions, but this is your first week, so I will give some. I will help you in terms of solving this question. Okay, so in this question, which is the correct retrosynthetic pathway for the following molecule? So this is what molecule we have, right? And how will be the retrosynthetic pathway for this one? So this is basically CHO, that's the formyl group, right? So that formyl group can be comes from, okay, so if you just do the disconnection, so what we get? We get the CH3 here, and here we get the negatively charged. So this negatively charge can be achieved from this bromo compound, right? Bromo or iodo, whatever it is, all are okay, right? So from the bromo, the CH3, right? So this is what we have. So we lock the first question, answer, sorry, first step here. Okay. So this will be the first synthon for the first part, the benzene part, and this is the synthetic equivalent. Now move to the another part. So the other part will be okay. So if we had some options like let's say HC double bond O and dimethyl like this, then this will be the correct one. But since in this case other coupling partner is not like this, then we will see all way around. So different way. So like whatever the disconnects that we did, we'll do the opposite of that one. So what we have now, so we just do like this. So let's say this is positive and the negative will be the other one. That is the C negative, CH negative, right? So this is what, and how we can get this one. So this we can get either from good link group. This should be the whatever here to get the positive charge on this position. We need to have some good link group. And if you look at the examples, what we have here, so we have the bromo, but bromo is not good living group. We have the iodo. Iodo is good living group, but yeah, iodo is good living group. In this case, this is not the good living group. Uh, okay, this is just a straightforward. No, if you just do the oxidation of this one, then we can directly get this PCC. PCC basically stop the reaction to the aldehyde step. Yeah, we don't really need to go into the disconnection because they haven't mentioned any disconnection. We just only need to focus on disconnection. They haven't mentioned like this. If you just do the functional group interconversion, that's it. So this alcohol, this primary alcohol can selectively convert, stop the oxidation to the aldehyde step by using the reagent PCC, pyridium chlorochromate. So this PCC, if you just use the PCC, we'll get the synthesis of this product done. So yeah, these all are waste then. No need to go into much more complication. So just this is good enough. So this alcohol, we can directly oxidize this alcohol to the aldehyde, and we can selectively stop oxidation to the aldehyde stage by using this PCC reagent. So that's also I need to highlight. So generally, it's difficult to stop oxidation of the primary alcohols to the aldehyde stage. But if you use the PCC reagent, it will stop at this aldehyde stage only. Right. So these are some concepts on the Umplong concept that we'll discuss in the later part of these some. But yeah, this by this way you can directly easily go into the we can easily get the final molecule just one reaction. So do you guys have any doubt in this one? Answer for question number 7. Okay. What is the question number 7 here? Okay. So we'll take the question number 7. Right. So what we have here? We have the in this if you look at the starting alpha beta unsaturated ketone and the another there is a ketone. right? And we add the NaOH, that is the base. So what does it happen when we add the NaOH to this mixture of this one? So basically, preferably this proton is getting abstracted. Do you know why? This is mainly because after abstracting the proton, we get the enolate, which is stable enolate. So what enolate we get on this one? O negative, this one, right? And once we get this enolate attacks on the in the Michael fashion on the I'll draw with the different color here. Okay, on this one. So this goes back here. This attacks here. This bond moved here, and this again goes here. So what we'll get here? We get like this. So this is now double bond. This is the O negative now, right? And this bond has attacked. So this is newly formed bond. This is the keto. Okay, this is what we get in the first step. In the second step, what do we get? So this enolate now can tautomerize, right? So I will directly skip one step. So negative. And now when it goes back here, sorry, I will just draw with the some different color. So basically we get the alcohol, that is the option A. That's what we get in this. Oh, sorry, one, two. So this will be the ketone here. Yeah, once this this bond attacks here, O negative, this O negative can then further abstract the proton, so it convert into the OH. And upon heating, I think this can convert into the alpha unsaturated sorry, the ketone as well, because there is the active proton. So this proton is active. So they have given particularly heating as well. So once a compound is formed, upon heating, so hydrolysis takes place to get the compound B. Okay, so compound B is the correct option here because reaction further proceed to the because of the heating, hydrolysis takes place. So we get the compound B as a product here. Do you have any doubt in this question? Okay, so if you guys don't have any doubt, we'll stop here for today. And hopefully, I will come with the better arrangement from the next week. I will try to sort out this how to write on the screen. So, okay, so see you on the next Tuesday then. See, yeah. So you can, those who don't have any doubt, they can leave. And yeah, see you on next Tuesday.